Hello, this is Paul from Force Attack. In this lecture, we're going to show you a new type of integral, which is the rational functions, and the method for that type of integral. So we will go back to partial fraction, and which is from pre-calculus. Remember, so 171. And the partial fraction method is very important to break down a complex rational expression. Okay, you remember that? It's a famous method. Okay, a few hundred years ago we already had. So here's a basic summary. I did not summarize the partial fraction here. Okay, so if someone you have questions, you go back to 171. Definitely we have all the information there. For rational expression, so we do a little summary. If we have a what is a rational expression first? Polynomial over polynomial. Okay, so that's rational. And the first type, if it's improper, okay, which means the degree of the top is more than or equal to the degree of the bottom. That's improper. So for improper, usually we need to do long division to convert it to proper one. Okay. So if we have a proper one, then it's a partial fraction. Okay, works. And it decompose into partial fractions. And so each fraction will be very easy to do integration. I will have a few examples to show you, okay, one by one. And for some partial fractions, I still show you the detail how to do. Okay. For example, the first. We'll look at this example. This is a rational fraction, a rational function, or rational fraction, because this is a polynomial, right? Even constant. This is a polynomial. Okay, so that's a rational. But how about this is complicated? We do not have any formulas to directly tell you what's the antidifferential. However, we do have what? Partial fractions to break down this into two easy fractions. So can we see? So the integral, if I break it down to find the partial fractions, break it down or decompose into partial fractions. What is the partial fraction? The first is 1, negative 1 out of x. The second is 1 over x minus 3. Okay, of course you ask, this is y equal to here. You can go to verify they exactly the same. That's the method from partial fraction. And I have detail, show you the next page. Okay, if someone you forget, go to the next page. I have all the details how to break it down or decompose that rational fractions to these simple partial fractions. If we have the simple partial fraction, you know what is the antiderivative. ln, right? Log. Okay, so we definitely get it. See, if I just copy that to here. Now, if we break it down to this partial fraction, now it's 1 to e, right? The first negative 1 out of x plus 1 out of x minus 3 and dx. Okay, if we do this now, we definitely know. Okay, we know the antiderivative for each one. For the first is negative ln absolute value of x. For the second is still the same. Okay, is ln absolute value x minus 3. Can you see? Okay, this is the antiderivative, and we use the fundamental is from 1 to e, and the prolog. See what do we get? Negative 1 plus ln parenthesis 3 minus e, because you know what is the value for e, 2.71812, like that. So this is positive, good. And then minus ln 2. We can merge these two together, right, by using the quotient rule of log. After we merge these two together is ln parenthesis 3 minus e over 2, right, and then minus 1. See, it's very easy to get it. Okay, very easy to get the integral. Okay, for this rational, but we definitely need to know how to do partial fraction. This is the most important one. the detail for the other partial fraction here, why this can be break down to this simple one. Okay, so everyone, if you forget it, so please follow me, go to all the details. So how do you get a partial fraction decomposition? This why? Because the first we look at the bottom. The bottom we can factor. We find the two linear factors. Remember the theorem of partial fractions. If the bottom factor are linear, so we have each fraction for each linear factor, right? The top is the constant number AB. So first we set up the equation 1. What we need to do is to find the A and the B, right? Okay, how to find it? Here is the basic. So we can times multiply by LCD, okay? And then we get the left is 3, the right is A times and the B times. Look at this equation, important. This is the most important equation. We call it the basic equation, okay? From this equation, we should find all the constant number A or B. We have a basic two method. The first is compare both sides. For polynomial, we can find all the coefficient for x or x squared. For each term of x, they should be equal to other, and then you can build a system of a linear equation. Remember that? Okay, that's the first method. The second method for this easy one, okay, the easiest method is the second. Okay, just plug in special value directly to find A or B separately. Okay, remember this. So if we want to find the A, plug B equals 0, plug x equals 0, we don't have B, right? And then use over A equals -1. If we want to find the B, plug x equals 3, so we don't have A, right? And then we direct this over B equals 1. See, easy to get A and the B. We plug it back to the first equation. See, that's the decomposition. Is the same, right? Okay. So now I will go to another questions. So look at the second. Can you see? How about this? 2x minus 3 polynomial, the bottom is still polynomial. So why I give this still the same? No, a little bit of difference, okay? Please show a little bit different. And I will get the partial fraction. The partial fraction is here. So the first is 2 over x minus 1. The second is minus or plus negative, okay? x1 minus 1, x minus 1 square. So do you think, so this term is a little bit, so we have a square, okay? Means this is the linear factor. However, the factor has a multiplicity. Remember, had the multiplicity too. It's only single power, has the power 2. I will definitely show you how to get this on the next page, but I will not go to all the detail, okay? So you can look at it later. So I'm directly going to this. If we have this breakdown or decomposition, how to do integration? Now, easy, okay? I plug in to this into the integrand. The first is 2 over x minus 1. The second is x minus 1 square, and then dx, right? Okay. Now easy. Why? Because the first is ln. The second, don't worry, the second is power, right? The second is a power function. Do we know the antiderivative for power function? We do, okay? And then we just do get the results. Easy. The first is ln, so we have 2, right? 2 ln absolute value x minus 1. Okay, this is a composite function. So if you use the chain rule, definitely will get that. So the second, if you change it to this is x raised to the negative 2's power. Okay, use the power function. So what do you get? You will get this 1 out of x minus 1. X minus a group is the other chain. However, the derivative of the inner is still 1. Okay, so the result is the same. You can go to verify. And then plus c, don't miss plus c. Okay, so look at it. If we know the breakdown, the partial fractions, very, very easy. And the next page, I'm going to show what the detail. Keep in mind that this is another type. If we have a multiplicity for linear factor, so here it is. Okay, and the linear factor, but with the multiplicity too. Okay, so the theorem tells us we have 1, okay, power 1 and the power 2, the same factor, okay, but power 1 and the power 2, and at the top is going to still the constant number AB, and then we use the same method. Okay. A little bit of difference, let's go over. The first term is LCD gets the basic function, the basic equation, and then I use a plug in special value. I can plug in special value x equals 1 to get b, right? Plug x get b is -1. Now I can another plug in, okay, easy. Or another is going to compare. Can we see this? B is -1, so the right is ax, right? The left is 2x. Okay, two polynomials got each other, the coefficient should be corresponding to each other. So 2x should be equals to ax, a should be equals to 2. And then we get what is the decomposition, right? Okay. A little bit of difference, okay, for linear factors. Now for any linear factor you should remember this method. But we do have another, okay, is not a linear factor. Can we going to see the last example? Can we look at this integral? So it's the polynomial over polynomial is a proper one, right? Because the degree on the bottom is greater than the degree on the top. And now I can directly to decompose is the same. Okay, I'll show you what is the partial fraction here first. And the partial fractions, okay, the partial fraction is this 1 out of x plus x minus 1 over x squared plus 4. Okay, and can you see this is a linear factor, this is not a linear factor. Okay, usually we call it quadratic. Okay, quadratic factor, that's another case. The detail I'll show you the next page later. Okay, data. Now I directly use this. Okay, so going to do the calculation of integration first. I will get that to here. So equals what? Equals integral. Now break it down to this. I copy the first partial fraction. The second partial fraction is here, x squared plus 4. Okay, easy to verify these two are the same, and then dx. Okay, the first we know ln, absolute value at x, right? How about this complicated? Okay, you can do like a directly substitute, but the best way is separate first. Okay, the best. See the top, the numerator we have two terms. Is better to separate or expand the fraction. Okay, we're going to, for the second term, we're going to do this. Expand the fraction. Okay. See, we have two fractions later. Why I do this? Because later you will see one by one. Okay, we resolve one by one. Each one will be easy. So the first we already have, right? ln absolute value, everyone know. The second break it down into two fractions. The first fraction is x over this, x over x squared plus 4 dx. Well, the second is minus 1, right? So minus integral 1 over x squared plus 4 dx. Okay. Now we just imagine. Is this easy to do? We did this before, right? If we do substitution for the bottom, if I put it here, we do substitution. Substitute this up here. Okay, u equals x squared plus 4. Okay, if we do this, see, easy to get it. And then what is x dx? We definitely find it, because we find that du is 2x times dx. See, x times dx, x times dx. So everything substituted to u. So this is good. So how about the second term? This we do have a formula varies close to this fraction. Which formula? Do you remember for this term? Which formula? Arctangent. Okay, this is a close but we need to manipulate a little bit. So we can directly use the formula for arctangent, okay? We have to manipulate a little. So I will show you how to manipulate. One by one step. The first I copy. The second I said to do the substitution, so I going to complete this substitute. Okay, so the bottom is u, so 1 out of u. What is x times dx? X times dx is 1/2 du. I said I was going to manipulate a little. Can you see what is no, this is a minus, sorry. So I have to minus which one? I will going to divide it by 4. I'm always do this. 4 I take it out into the coefficient, which is this integral. Now the integrand goes to x over square over 4, which is x over 2 square, and then plus 1, and then dx. Okay, I just do this kind of manipulation. Now we see what? We see this term definitely goes to what? Oh, I say this. We do have a formula for antiderivative. That's what we said before, right? Arctangent. So what is that? Is 2 times arctangent at x over 2, because this is a composite function. So we take a derivative. You should use the chain rule. Okay, I did not include the coefficient. Okay, so 1/4 times 2, later it will go to 1/2. Okay, now I will get the answer. So this and this we get the answer, right? This is easy, ln, right? Okay, so plus 1/2 ln absolute value of u. So this we said in minus 1/4 times 2 is 1/2, and this is the arctangent at x over 2. See, and then plus c. Don't stop at here. What this is u we need to do. See, this is a u. We need to do back substitution. So we back substitute, we get a ln absolute value x and plus 1/2 ln. What is the u? X squared plus 4. So we plug in. No, sorry, x squared, okay, plus 4. And this you cannot see. And then what is just copy 1/2 arctangent x plus 2 plus c. Yeah, that's the answer. We look at it very long. Okay. However, the method is straightforward. So the only thing we need to do is the partial fraction. So I will going to see. There's a little bit. Okay. Can you see what the difference? When you compare to the previous? So this first we need to find the factor, okay, of the denominator. The factor is x. That's linear, good, but this is not a linear. Actually, it's called a quadratic factor, right? Okay, so we have a 2. If we break it down, we have a 2. Okay, have a 2 fraction, partial fraction. The first is for the linear is this term, right? Remember, so this is something new. And now the term for the top is a linear term. Okay, for any quadratic factor of the numerator should be equal to a linear term bx plus c. And then we look at the ABC, going to solve. Here is the normal way we're going to solve. I did not make a system of linear equation. If you like, you can make a system of linear equation, okay, to solve the linear system. Or we can do this, plug a special value. But whatever, the first we need to go to basic equation. Times LCD, go to basic equation here. Okay, I plug in the special value. When I plug x equals 0, I can ignore b and c, right? Goes to only a. Plug x equals 0, I get a. If I get a, how to get the b or c? Remember, compare the terms of x, right? I'll compare the terms. If you find the b times x squared, so b is the coefficient. Oh no, So a plus b, the coefficient of x squared on the right side should be because it's equal to the left side. See, the left equal to the right, we get b equals 1. The same for c. C should be a coefficient for x term. So we compare the x and the x. X to the left is this, x to the right is this, so we get a c. See, we get A, B, C, and then what do we have? We do have the decomposition. So this we proved the first. That's all. Thank you.